logistical challenges, please contact Martina, me, or Jan. And Katie will be here tomorrow, so thanks to Katie, this is actually, and also Karen. Karen will be the big person in our sessions for any logistical challenges. What do we have to do today? Okay, so we have talks all the way to about 12, nearly 1 o'clock. Lunch is on your own this week. For those who were here last week, you were wondering where is the lunch. There are a bunch of lunch places around campus, but you can also go further into town if you like it. Uber works here, so that's what I did this morning. That's really late. And what else? The reception is tonight. I think 5:30. 5:30. Okay. And then we'll just downstairs.
No, I think that if the weather is nice, it will be outside Nordita. So outside the building where you registered.
It's the yellow building.
Otherwise, inside here in the main room. But I hope the weather will be nice enough to read out.
And also, supposedly the legend has that Nordita building used to be a hospital that treats infectious disease. So we should all go in there to do some research in the afternoon. And you have already heard that there are offices inside Nordita Institute that you can work there, your desk and stuff like that. And you have cards to access. For those who came in last week, like me, you might not have cards. And we can talk to Karen in a session about it later. What else? I think dinner's on Wednesday.
And all the other information will be posted online in the main page if we have no announcements.
Yeah. But we'll probably remind you of the nurse where and all that stuff. But any other questions you can ask us. One big thanks to Martina and John and Karen, and did a lot of the evaluation of organizing. We pretty much did nothing except complain. So thank you, and thanks for coming. Welcome to Stockholm. And tomorrow I talk about us to cross correlations with perturbation theory for CMB lensing modeling.
Thank you. So my apologies to those who heard exactly this talk last week. Maybe there'll be something new you can get out of it this week. This is some work that we've been doing over the last roughly couple of months with Sharad Modi and Mohamed Blah, both of whom are going to be here all week, same as I am. So if you have other questions or anything, you can track any of us down. It's out on the archive if you use the Magic Archive. And this talk is slightly more aspirational than dealing with current data. We're trying to think a little bit about how wonderful the future is going to be and how we could rise to the challenge of analyzing data that we hope will start pouring in. So I want to start by just giving a really, really quick, rapid overview to sort of set the context for what we started thinking about of lensing of the CMB. Now, of course, we all know that the anisotropies, the primary anisotropies we see in the CMB, are the seeds of all the large-scale structure that later forms in the CMB. And there's an interesting fact that, right, once you tell me the expansion history and the constituents of the universe, once you know the seeds, general relativity makes a unique prediction for how large-scale structure should grow over time. And the large-scale structure that then grows gives rise to gravitational potentials, which lends the very photons that give us what the statistical behavior of the early universe was. And so this provides an important consistency check on the theory and also sensitivity to late-time physics. And it's going to be this sensitivity to the low-redshift universe that I'm going to want to explore in this talk today. So this just shows you a map of the lensing potential from Planck, the 2015 lensing potential map. This is essentially a map of all of the matter in the universe, which is actually kind of cool. The thing that's interesting about this is not that Planck was the first experiment to measure lensing, because it wasn't. It also wasn't the first experiment to measure lensing by large-scale structure, nor was it the first experiment to measure lensing of the CMB by large-scale structure. So what is it about that Planck map that's interesting? Well, one of the things that's interesting about that Planck map is that for the first time, Planck made a high enough resolution, high enough signal-to-noise map over enough of the sky that lensing actually became competitive with primary anisotropies in terms of constraining things, right? So for the first time, the experimental error bars from Planck were smaller than the theoretical error bars from just saying, let me assume lambda CDM and put the parameters some other way. So the thing that's interesting about this is that we're going to look back and see Planck as a kind of coming of age for CMB lensing, right? Pre-Planck, it would have been some very, very loose consistency check. Around about the time of Planck, it's driving parameters at kind of the 1 sigma level. the future for pretty much all CMB experiments will be that a larger and larger fraction of all of their science will come from CMB lensing, right? So this will be a turning point. And even in a few years, we'll look back and kind of laugh at how primitive and low signals and noise Planck would be.
So the current error on the sigma 8 derived from CL55 smaller than like the difference between the prime primaries and like the low Z lensing, or is it larger than that difference?
It's smaller than, but not by a large amount.
No, but it's smaller.
But it is small. Right? So there you go. So looking forward, right, at the landscape, we know that there's this large number of experiments that are being proposed, planned, or in construction right now to constrain primordial gravity waves from CMB polarization. And a very natural byproduct of exactly those things, without needing any extra data, is that they make spectacularly good lensing experiments, right? And so CMB lensing, like all kinds of lensing, right, is sensitive to the total matter field, and because it uses relativistic traces, it's sensitive to the space-space metric perturbations, so you can use it to do the same kinds of things as we typically want to do with cosmic shear or galaxy-galaxy lensing, or whatever. And it has very, very different sets of systematics and different behavior than, for example, cosmic shear does, right? So it provides a really nice consistency check on the same physics. For example, one systematic you don't have to worry about is photometric redshifts. The CMB redshift is really, really, really well known. The downside of that is it's really, really, really hard to change. You have to wait an awfully long time. CMB lensing surveys tend to have very, very large sky fractions compared to, say, a galaxy survey, but relatively poor resolution, right? We do not talk about sub-arc second scene when we discuss a CMB lensing map. The lensing kernel is peaking way up at high redshift and has power to very high redshift, all the way out beyond redshift 1, where galaxy lensing becomes increasingly difficult. Right? So we're talking about large sky fractions, low resolution, high redshift. The CMB, it turns out, is a background. That's what the B means. And so it's basically behind pretty much everything in the universe that you might otherwise be interested in. And that means that everything contributes to some extent to CMB lensing. That's fantastic, because it means that if you are interested in peculiar object X, it probably lends the CMB to some extent. The problem is that if you're not interested in object X, it probably lends the CMB to some extent, and you've got to deal with that, right? Projection is a really big deal. So, the sky giveth and the sky taketh away, but we end up with a data set that could in principle be used for a bunch of things. I won't go through them because I'm sure everyone knows, but on the same time scale as we're busy spending taxpayer money building these CMB experiments, we're busy spending even more taxpayer money building all these optical imaging experiments, and they're going to be great, so the story goes. We're going to map very large areas of the sky to unprecedented depths. And so the question that we were kind of interested in, is there any sort of combination of these different types of surveys that can be more than the sum of their parts, right? Where can we kind of use synergies between these things? And we were interested in using this possibility of doing cross-correlation between the galaxy surveys and the CMB experiments to test general relativity, probe the galaxy halo connection, and the example I want to walk you through today, try and measure the growth of large-scale structure. And so what we're going to try and do is use the fact that in the optical survey I have actual redshift specificity. I may not know the redshifts to 10 to the minus 5, but I probably know them much better than I know where along the line of sight a particular lensing event happened. And so I'm going to be able to use the redshift survey or the optical survey to isolate where in redshift the kappa signal came from. Because I'm not going to autocorrelate kappa, but cross-correlate it, I'm going to get a huge increase in signal to noise, and I'm going to downweight a whole bunch of systematics. So that's going to be the goal. And, it's a truism that every time the data get better, we need to improve the theory at the same time if we actually want to get out the science that we write down on our white papers that we want to do. And so the question we were interested in addressing and thinking about and just kind of mulling over is, what's the right framework for analyzing CMB lensing data, right? That's kind of where we were wondering. And just to set the kind of scales and level of sensitivity that you need, what's shown here is the angular power spectrum versus L, right? So small scales to the right, large scales to the left. This is a few arc minutes. This shows you the clustering signal for 10 to the 12 solar mass halos at redshift 2 in a slice of about delta Z of a half around redshift 2. This shows you the same thing at redshift 3. The red curve shows you the kappa auto spectrum. And then the blue curve in between is the cross spectrum between kappa and these halos, right? Just to give you sort of a feeling. These green and red dashed lines show you the shot noise associated with the gold sample from LSST, just to kind of, give you some feeling. And the red line shows you the kind of noise you might expect from one of these, very future CMB stage 4 experiments. So you can see that we are sample variance limited up to L of about 1,000 in lensing, and then at redshift 2, we're sample variance limited to, very, very high L, and at redshift 3, you see it starting to cross around L of 2,000. These noises are per L, and there are thousands of L's here, so it's slightly more useful to plot the fractional error on the cross spectrum and the galaxy auto spectrum in bins, right? So here I've averaged things down not per L, but in bins of L. And there's, a little over a dozen points there, and the error bars are at the, a couple of % level or smaller. So when you average them all together, you can make a sub% level measurement of these spectra at redshift 2 and at redshift 3, and, I can plot it at redshift 4 and 5 and so on, right? So the goal here is to be able to model things, right, on scales out to L of, say, 2,000 or maybe 2,500 at about the % level. That's roughly what it is we're going to try and do. So here's an example of the kind of science you could do from that. Here's an example of trying to measure the matter power spectrum, right? So I think everyone here would agree that trying to measure the growth of large-scale structure is one of the kind of premier goals of cosmology. And so I'm going to interpret that to mean I want the matter power spectrum as a function of k and z, right? That will be my goal. And schematically, I can measure this matter power spectrum by picking a bunch of galaxies at redshift z and performing the following incredibly complicated algebraic operation, right? I'm going to write the matter power spectrum as b times p all squared divided by b squared times p. Do I need to work through that more carefully? Okay, all right. It's early. All right, so now I can absorb one of the b's into here to turn an m into an h to get the matter-halo cross-correlation, two b's to get a halo-halo autocorrelation function, and then making extremely liberal use of the twiddle, I'm going to say, well, halos are the same thing as galaxies, and kappa is the same thing as the mass, and power spectra are the same thing as projected power spectra, right? Twiddly. It's astronomy after all. And so I can get information from the matter power spectrum by taking this sort of ratio, right, of the angular power spectrum of the cross spectrum squared divided by the auto power spectrum of the galaxies.
Martin, actually, is there not a subtlety here? Because what you measure is the projection of the numerator and of the denominator, so you measure the ratio of two integrals, but here this would be sort of exact if you had this whole thing inside one integral, so you were taking this whole thing and projecting.
Does that no step here does an equal sign up here.
Do you think that really matters, though, or should I just...
No, because I would never do it this way. You would never do this. We're all on the same page, right? Do not ever do this to the data. This is horrible. You would never do this to the data. Zach, would you do this to the data?
I mean, I won't.
Okay.
Fifth Amendment.
All right, so what you would actually do is you perform a joint fit on the data, right? You would never actually do this. So if I only had the auto spectrum of the galaxies, right, the reason I can't go anywhere is that there's a huge degeneracy between the amplitude, which I'm going to just write down as sigma 8, and the parameter, the bias, b, right? I can't split them if I only have the auto spectrum. But if I have the cross spectrum and the auto spectrum together, I can break that degeneracy, and I can measure sigma 8 and b independently, right? And so, in order to make progress, I would not do this division. I would come up with a model for the auto and the cross spectra. I would fit them, and I would get sigma 8, right? And then I would move to a different redshift. I'd do the same thing, and so on and so forth, right? So, in order to make progress, I need a model for the auto and cross spectra of bias traces, right? So, I need to predict the auto and cross spectra of bias traces, and since this is the CMB and since this is high redshift, your first thought would be, look, I'm at high redshift, I'm on large scales, let me use linear perturbation theory. Very unfortunately, that doesn't work. Linear perturbation theory is actually not quite accurate enough, so I need to include nonlinear corrections, and this is kind of where you start that, downward spiral into hell, right? Because nonlinear corrections, scale-dependent bias, stochasticity, all of the things that, make life difficult now raise their ugly heads, and we have to actually work through and do some real work. So what is the standard way that people in the field analyze these kind of data? Because lots of people have cross-correlated CMB lensing maps with their favorite objects. So the most widely used model is that you take halo fit, which is a fitting function based on n-body simulations to the matter power spectrum. It's computed automatically for you by Kamen class, which I think is a major reason why people do this, right? Because you can't sort of help having this file dumped on your disk. And then for now, most people just assume a scale-independent bias. That's right on the hairy edge of actually being allowable right now. and it certainly won't be good enough for the future. So what might we do in the future? Well, if you just kind of think about peaks theory, you could say, let me take b, and rather than writing it as a constant, let me write it as a constant plus a k-squared term. I'm superscripting these b's here with an e to indicate this is sort of an Eulerian bias model. Later on I'll want to have a Lagrangian bias model as well, and I want to keep them separate. If you actually just plot from n-body simulations what the function looks like for the bias, you find that it's actually better fit if I include a linear in k term. There's zero theoretical justification for that. It's totally phenomenological and made up. But I'm going to allow myself the freedom to have a constant, a linear in k, and a quadratic in k term. And I'm going to write down the following thing, that the cross spectrum of matter and halos is going to be 1 power of bias times p halo fit, and the auto spectrum of the halos is going to be 2 powers of bias times p halo fit. Now, for those who haven't already seen the talk, let me tell you that the important assumption here is that the halo-halo auto spectrum bias and the matter-halo cross spectrum bias are the same. That assumption is wrong. But I need to make some assumption because I need some parameters that allow me to simultaneously predict the auto spectrum and the cross spectrum. And this sort of simplest case is that this goes as b and this goes as b squared. And we know that's not true, but I'm going to assume it anyway. So if this is the standard model, what's the better model? What should we have done? Well, I'm glad you asked. I'm working on large scales and I'm at high redshift. This sounds like a job for perturbation theory. I can't use linear perturbation theory, it's not quite good enough. But almost any other perturbation theory actually turns out to work pretty well. There's a lot of perturbation theory techniques out there. The one that we decided to use was the one we've been working on for the last 4 or 5 years. We've got this Lagrangian perturbation theory framework that allows us to do a bunch of things. It naturally handles autocorrelations and cross-correlations. It works in both real and redshift space, although we only need the real space version for this problem. And you can do it in either Fourier or configuration space statistics. You can do power spectra or correlation functions, and it all works with exactly the same parameter set and everything, so you don't need to come up with a brand new theory every time you decide to change your statistic. So here's an example of what it looks like. There's some matter-galaxy cross spectrum. It involves some tree-level terms and some one-loop terms, and then some parameters that tell you kind of how biased the objects are. And so this is a scale-independent Lagrangian bias. This is a sort of a B2 or a scale-dependent bias, and so on. And so the cool thing about this is that, one of the great things we all love about the CMB is that, you can open up a textbook, you can start with, Einstein's equations, and you can derive the CMB. It's about the only problem in cosmology where, with a pencil and paper, you can derive something meaningful about, something that we observe. And so this is sort of the simplest extension, right, of just going beyond linear perturbation theory, including the second order term, right, and actually being able to do something, right? So it extends this linear perturbation theory analysis, but stays fully analytic, which is really, really nice. So how does it do? Well, just to show you, here's a comparison with n-body simulations. I'm showing the power spectrum here as a function of k. Just to set the stage, this is the angular scale of L of 1,000 to 2,000 and 3,000 at redshift 2. Redshift 2 is the peak of the CMB lensing kernel, that's why I chose redshift 2. And these points up here show you the auto spectrum of halos in this series of n-body simulations for 10 to the 12 solar mass halos. This is the mass auto spectrum, and this is the cross spectrum between the halos and the matter, right? So that's what the n-body points look like. And then these lines show you the predictions of linear theory, halo fit, for now with a constant bias, so we can kind of disentangle what's due to bias and what's due to nonlinearity. I'll reinstate that quadratic form a little later. And then perturbation theory, where I'm allowing the bias to be nonlinear. So this is a little bit unfair because I'm saying halo fit has a constant bias, but perturbation theory is allowed to have a flexible bias, but I'll free everything up in just a second. So what you can see is that linear theory does really a pretty poor job for any of these statistics, even at redshift 2, even below k of 0.2. At first I found this kind of surprising, but if you just do the numbers, it turns out that that's exactly what you would have expected if you had sensible expectations. So even by k of sort of 0.2 or 0.3, you're 25% off. That's no good. We do not do precision cosmology that way. What's interesting is how bad this constant bias assumption is, right? So you can see the green line is doing a very good job of passing through these points for the matter, but it's doing a pretty bad job for this cross spectrum. And here I'm showing the ratio just for the cross spectrum, right? You can see it's off by sort of, 10%, even at L of 1,000, right? Not because it's off in the matter, but because the bias is off. And then if I plotted the auto spectrum, which comes in as b squared, it's even further off, right? So constant bias is bad. Yeah.
So Martin, are you actually matching halos to the n-body here, or is this, I mean, you must be if there's bias involved.
Yeah, this is halos. This is the halo auto spectrum, the halo matter cross spectrum, and the matter matter auto spectrum.
So what are you doing to do that? HOD or like?
This is just halos. I'll put galaxies in a minute. This is just halos.
Oh,
And you can see perturbation theory does spectacularly well. Right? Perturbation theory is clearly correct.
But this badness of like a linear bias halo fit model presumably is different for different like halo samples, right? Because your
Right.
curve has like a bias of 3 or something, it looks like.
It's a bias of 2 and a bit, right? So one of the things, right, is that as I go to high redshift for the objects that I can actually measure, like quasars and LDGs and those kinds of things, we are talking about things around 10 to the 12, maybe 10 to the 11 and a half, maybe 10 to the 12 and a half, but they become increasingly biased. And that is one of our points in the paper, is that, you have to go to extremely faint objects to get down into the sort of B of order 1 regime. Once the bias is big, its scale dependence is big, right? So, I mean, it's not a surprise that it's scale dependent. That's not the surprise, right? It's kind of a little bit surprising that even at very low K, this is sort of a big deal, right? So this is redshift 2. You can also look at this at redshift 3 and at redshift 1 and half and 3 and a half and so on. Things look really, really good at high redshift for perturbation theory. They get increasingly worse, right, for the other methods, and that's exactly Neil's point, that as I'm going to higher redshift at a fixed halo mass, these things become more and more biased, and thus the scale dependence of the bias becomes worse and worse. As I go to lower redshift, then what you see is perturbation theory starts breaking down, right? I have to work to lower and lower K, or larger and larger scales, for perturbation theory to remain a good approximation. Now, obviously, I could go to higher order in perturbation theory, and that would help, and so on, but this is just showing you one loop perturbation theory. And so I wouldn't be able to push this down to redshift, 0.25 or something like that. There, it's not going to work. Okay, so this just shows you that these models sort of work in terms of halos and things. So here's the question we asked. Let's consider a future experiment. It's basically going to be, I read the white papers that have been written by the LSST and CMBS4 groups. I kill myself laughing for a while, but then I suck it up and I say, no, this is clearly truth. I am going to imagine cross-correlating a CMB lensing map with the gold sample of galaxies from LSST, because of the white paper could never lie, in a redshift slice of a half at redshift 1, 2, and 3. For those of you who don't have these things memorized, that's an I-band limit of 25.3, these parameters for the CMBS4 experiment. And I'm going to compare these two models, right? Models in quotes, because this is just a series of fitting functions, but halo fit, right, times this fully now quadratic bias. I'm going to allow the full flexibility. And perturbation theory with these scale-dependent biases that were there originally. And I'm just going to concentrate on measuring one number. I'm just going to measure sigma 8, right? So I'm going to integrate out the scale dependence and imagine that I somehow knew the scale dependence from Planck or something. So I'm going to jointly fit the kappa galaxy cross spectrum and the galaxy galaxy cross spectrum, right? And I'm going to ask how well can I constrain sigma 8.
Sorry, I'm just curious, is the reality stretching thought that you get redshift to these galaxies at beyond 2?
The reality stretching part is that I just assumed that everything that was written down in those white papers was going to be how the instrument performed. So there's like no foreground subtraction in here. There's no, actual reality. Right? Similarly, that these galaxies will just come pristine and blah blah blah. So those kind of-
Martin, is that an effective beam for CMBS4? Or is that at a specific frequency?
This is actually 150 gigahertz, but yeah. You can think
And
of
you're
it.
assuming perfectly clean then at 100.
This is complete. Right. So this number is completely clean. Now, it doesn't really matter too much what you do here on the noise. On the beam. It does matter a little bit what you do on the noise, but it degrades gracefully, right? So nothing I say is going to depend on if I've written down 2 or 3 microcolor, and you would be just as happy. Right? So this is actually kind of interesting. So let's just focus on the lower panel, right? So at high redshift, perturbation theory works really well. At redshift 2, it works really well. Redshift 1, you can see it kind of starting to depart a little bit from truth. This is sigma 8 in the simulation, this vertical dashed line. And then the fits from perturbation theory are these red lines, and you can see it's working relatively well. The blue lines are much tighter. They are from the halo fit times this flexible quadratic bias. So they're much, much tighter, but you'll also notice they're very, very biased, right? So this assumption that I can use the same bias parameter in the auto spectrum and the cross spectrum is completely false. Right? You just can't do that. You can even go into the n-body simulation, and it will tell you can't do this if you ask it nicely. But the bias model that we've assumed in perturbation theory naturally knows how to deal with that, right? It knows in what way the autospectrum and the cross spectrum differ, right, using the same underlying parameter set. So this is actually kind of cool because it means that the perturbation theory works, at least at high enough redshift, right? It's not quite as tight as you could have gotten if your fit had been perfect. But on the other hand, it's not doing too badly. If you actually go through and measure the widths of these things, you can get a sort of percent level measurement of sigma 8 in each one of these redshift slices, right? So overall, you do very, very well at measuring the growth of structure.
So why is the error bar bigger for red than blue?
So it's a very, very, very constraining assumption to assume that those two bias parameters are the same, right? And so if I just come and look at the fits, right, this is what happens in the fit. So these orange lines show you the auto and cross spectra for the halo fit model, and the green lines show you the spectra for the perturbation theory model. And what you can see is the way that halo fit gets its fit is it kind of overshoots and then undershoots, and it kind of balances that out, which is why the answer is wrong. But now you're fighting a growing and a falling likelihood, and so you get a nice tight result, right?
Oh, okay, so the error bar is small for the blues because the fit is bad.
The fit is bad, and you can see the fit being bad here, right? So, well, I mean, it's a very expanded axis, right? But here's what the perturbation theory thinks the fit should be. We fit it up to LO2000, but you can see it kind of more or less works even out to 2700. But you can see that the way that halo fit is getting it is by kind of balancing this overshoot with this undershoot, right? And the same here, except here it's the opposite spectrum goes off, right? So the delta chi-square between these things is actually quite large, right?
But the number of parameters though for the red and the blue are the same.
Almost the same, right? The blue is 4 and 4 plus sigma 8, and the green is, red is 3 plus sigma 8, the green is 4 plus sigma 8. There's 100 degrees of freedom, there's 4 or 5 parameters.
So I missed something, Martin, because you had the halo fit was a scale-dependent V1 on the previous slide. That's a scale-dependent V1, and the perturbation theory has a V2.
There's a B1, a B2, and hidden in here is a B sub k squared.
But there's no k dependence on those guys?
These are just numbers. The k squared p of k piece is in here. It's degenerate with the EFT correction. So we just call it alpha.
And for the perturbation theory, you didn't need to use a k term?
No. So the k term is purely phenomenological. It can't be real. But
Yeah. No, I know. I know.
So if we were able to model all the bias parameters in terms of V1, we would get even better constraints than the blue ones.
Oh, totally. If you told me, the relationship, how bias works and what B1 and B2 are, yeah, then things would really tighten up. Or if you can give me some priors on these things.
But that's not totally crazy, right?
It's not totally crazy, right? So I'm already at 1% just doing one loop perturbation theory with everything free. Clearly there's a lot of ways you could make this better.
Martin, why does the halo fit wrong model perform so much better at redshift 2 rather than redshift 3? You kind of expect as you go to...
So you always expect there'll be some point where things are going to roughly work because, as I go to low redshift, things get more nonlinear. As I go to high redshift, a fixed halo mass gets more and more biased. There's some sweet spot where those two have a minimum. Right? So part of this issue with halo fit is actually the fit to the matter power spectrum. It's only good to sort of somewhere between 5 and 15%. And the error bars I'm assuming here are like 1%. Right? So it's 5 sigma off just to begin with. But a lot of it, most of it is actually with this B of k assumption. The auto spectrum and the cross spectrum don't have the same B. So, the message we were trying to give in this paper is that at high redshift, modeling this bias is at least as important as modeling nonlinear structure formation. Everyone gets really, really excited about a better halo fit. But bias really matters, right? And the minute that bias matters, you can't just put in a number B and think you've solved the problem, right? So if you think about this in this EFT language, which is kind of a nice way to think about some of these things, as I go to higher and higher redshift, this nonlinear scale is shifting to higher and higher k. But the scale associated with halo formation, this Lagrangian radius of a halo, if I pick a fixed halo mass, that's a constant. And so K and L is going to gradually shift out beyond K halo, and K halo, the EFT expansion in bias, is more important. Right? This is what I was just saying earlier. In general, there's a sweet spot where B is not too scale dependent, but the nonlinearity is not too bad. Right? But hitting that sweet spot is not always easy. And we didn't really investigate it, but if I start picking weird samples like emission line selected galaxies or something, then exactly how this behaves could be kind of interesting. So let me just quickly go through a couple of future directions and then stop. Obviously, everything we did was to one loop. We can obviously work to lower redshift or to higher L if we go to two loop. It's not that hard to add things like neutrino masses, modified gravity, these relative velocity effects. These things are known. How to do it, you just need to do the algebra. You can include all these baryonic effects on small scales, which you don't really need that much at one loop, but you can do them as you go to two loops with EFT techniques. Something that Marcel and Urash have been doing is looking at things like FNL and non-Gaussianity constraints by going to low L rather than pushing to high L. There's an awful lot of volume out there at high redshift, and so it's really good for constraining large-scale physics. The whole thing works in redshift space and real space, so everything I've done is in terms of a photometric survey, but you could imagine doing this with a spectroscopic survey. Then you can work to lower K and have the same number of modes, right? There's a trade-off there. I talked about isolating a given slice by cross-correlating a redshift slice of galaxies with the CMB. You can do sort of subtractive color rather than additive color by cleaning out all the low redshift stuff, by cross-correlating the CMB with the galaxies at low redshift and then subtracting that contribution. That isolates the contribution only from high redshift. To do that, you need to know this cross-correlation coefficient. One of the cool things is that the perturbation theory actually naturally gives you that cross-correlation coefficient, so that's kind of neat. You can simultaneously fit the redshift distribution of the galaxies and sigma 8 using clustering redshifts. So I have a spectroscopic sample, an imaging sample, and the CMB lensing. Right? And the cross-correlation of spectroscopy with imaging gives you the NDZ, and the cross-correlation of kappa with the imaging gives you the bias. And you can just fit the two all together. That's very nice. And the nice thing is that the same formalism handles the spectroscopic survey, the imaging survey, and the lensing survey. Right? That's just kind of cool. So you have a joint parameter set. And then the thing we've been looking at a bunch recently is these multi-tracer techniques, which help you break a lot of the biases if you can actually get some reasonable range of luminosities. So let me finish, because I think I'm almost out of time. I think we're on the cusp of a fairly dramatic increase in both the CMB and imaging data quantity and quality. Certainly for the CMB, we're expecting the maps to get 2 orders of magnitude better, right, which is not a small step forward. The combination of the CMB and these galaxy data can be a lot more than the sum of these parts because they can break each other's degeneracies. Better data requires better modeling, or at least different modeling if you can't do better. With primary anisotropes, we're a little bit spoiled in that linear theory was essentially the whole story, right? As you go to lower redshifts, this is no longer the case, but it's still not hopeless. You can still do an analytic ab initio type of calculation. You need to model both the nonlinear matter clustering and you need to model for the bias. You need something relatively sophisticated. The current fitting functions for the matter power spectrum are good to between 5 and 15%, depending on exactly who you believe. But the error bars we're talking about for even next generation surveys are starting to become smaller than that. So these fitting functions basically just aren't good enough. Once B is not a constant, it is also true that the halo-halo auto spectrum and the matter-halo cross spectrum do not have the same bias. Don't believe me, just pick your favorite n-body simulation and plot it, and it's miles off. But this combination of high redshift and large scales for CMB lensing makes this whole thing an attractive problem for some kind of analytic or perturbative attack. And so you're basically doing something almost as ab initio as you're doing with primary CMB anisotropes. Okay, thank you.